So here is a model answer for the table of data. First thing to notice is that in the instruction it asks you here to find values for L in the range 40 centimeters to 80 centimeters. And notice this is very close to the lower end and this is very close to the top end. You must make sure you cover the full range as specified in the instructions. The other thing to notice about the length column is that every length is quoted to the nearest millimeter. So that's very important because, of course, you are expected to use a meter ruler and that level of precision is expected. Moving across now to the number of oscillations column, small n. Notice the number is adjusted to make sure that the timed raw data is at least 20 seconds. Here is the timed raw data, the first trial, and then next to it the second trial showing the repeats. Realistically, it should really be only given to 3 figures because, of course, human reaction error is within the tenths of a second column. This hundredth of a second column is meaningless. Once the average is taken of these two numbers, the number of oscillations, 20 in this case, is divided out to give you 1.28. So again, it's given to 3 significant figures. That really should be following on from the 3 figures gained here. And of course, if you square it, you keep the same number of figures again. So always keeping 3 figures for the raw times through to the calculated value of t squared. The last thing to notice is that every single column heading has the correct unit specified next to the quantity. Okay, and here is a model graph. Notice first of all the axes are labelled clearly with the quantity and the unit, in this case t squared and seconds squared, and the length down here in meters. Then the drawn points are clearly visible, little x's are preferred. The best fit line is a nice thin pencil line, and it's clearly the average trend through the middle of the points. Then the gradient calculation, the points used are marked clearly on the graph, both the lower point and the upper point. Then the calculation is done. On the margin here showing the rise, and here is the run. Notice that this hypotenuse here of this marked up triangle that is used to calculate the gradient is at least half the length of the best fit line. The scales are marked every 10 small squares at least. The vertical axis is marked every 5, but you need to at least mark every 10 squares to make sure you don't lose easy marks. Once you've calculated the gradient, you are expected to then use that number, which is basically the average trend of the data, to calculate a nice accurate value for any constant in the experiment. In this case, in this experiment, you're asked to find little g. So little g, of course, the acceleration due to gravity on Earth, is what you're asked to find. You've given this equation here. Notice it's already in the shape of y equals mx plus c because you plotted t squared on your y-axis of the graph and you plotted L on the x-axis. Whatever constant is in front of the x-axis must be the gradient. In this case, it's 4 pi squared divided by g. So you're expected to recognize that, find how the gradient is related to your constant that you're trying to find in the equation. So in this case, it's very simple. We just say this, you get a mark for saying that, and then rearrange it, put your number in, 4.08 was this particular data set, and you calculate the value, keeping to the same number of significant figures as you have been throughout. So in this case, 3. Give the unit and